Hello, my dear friends. I am Professor D. Chitrivedi. I am going to teach you about encoders and exclusive OR gate. Previously, you have studied about multiplexer, demultiplexer, decoders. In a decoders, many decoders you have studied. That is BCD to binary decoder you have studied, or BCD to decimal decoder you have studied. Now, we are going to study about encoders. What is the difference between encoders and decoders and why they are required in our digital system? Decoders, it means it is decoding the code or it is decoding the number system which the normal person can understand. That means the computer or digital system which can understand either it is a binary, hexadecimal, octal number system or some kind of number system which is in the form of 10, and normal person can understand a decimal number system. So the system which can convert from either of the binary, hexadecimal, BCD or octal into the decimal, that is known as a decoding the things, and it is required when it comes to the screen of the computer or digital system, so the normal person can understand. Opposite to that is called encoder. Encoder means the machine language. Machine can understand, because machine cannot understand normal decimal number system or alphabets. So the normal number system should be converted into the form where the machine can understand. That means you have to encode it, the number system and alphabet, etc. So the machine will understand. Encoders. Now, what is the actually the definition of encoder? What is the meaning of encoders? An encoder converts an active input signal into coded output signal. That means it will be having a decimal number system, let us say. Then decimal number system is going to be converted into any other BCD number system, binary number system, like that. That means the input will be having m number of signals, or sorry, so there are n input lines, only one of which is going to be active. Internal logic within the encoder converts this active input to a coded binary output with m bits. So this is normally just a block diagram of encoder. Here you can see that there are n input signals will be there. Out of this n input signals, only one of the input is going to be active at a time. So out of this signal, one of the input is either low or it is going to be high, and it is made different from other inputs. Now, according to this one, inside that there is a circuitry which is converting this thing, active input signal, into coded output signal, and coded output signal may be of m bits. So m output signals are required. So this is just a block diagram of encoder. Now, the first things which we are going to study is decimal to BCD encoders. We have seen previous lecture that initially the computers were utilized the BCD number system because it was easy for arithmetic, etc. at that time. Nowadays it is outdated, but still we are using in some cases. So we have to convert a normal decimal number system, which is main language, layman can understand, everybody can understand, that should be encoded into the form of BCD, binary coded decimal, so the machine can understand and it can perform the arithmetics. So how that can be done? That can be done in a circuitry with some gate and switches. Figure 4.25 shows a common type of encoder, the decimal to BCD encoder. The switches are push button type of the switches, like those of pocket calculator. And I'll show you, this is a normal decimal to BCD encoders. You can see that. Here there is a plus 5 volt supply is given, positive terminal of the battery is here connected to one end of this push button switch. This is kind of push button switch, and this is a normally a line, different line for 0, 1, 2, 3 up to 9. Zero line is not connected to any input of the OR gate A, B, C and D. One input. That means only this OR gate is having only one input is going to be high. When this switch is going to be closed, what happens? This plus 5 volt will be coming on this line, otherwise it was 0. So plus 5 volt means it is 1, binary 1. It's going to be coming over here, and one of the input of the OR gate is going to be high, so output is going to be high, and that way this circuit is going to be working. You can see that the switches are push button switch like those of calculator. When the button 3 is pressed, the C and D OR gate have a high input, and therefore the output is ABCD is equal to 0011. If button 5 is pressed, the output becomes ABCD is equal to 0101. When the switch 9 is going to be pressed, ABCD is equal to 1001. See, if button 3 is going to be pressed, that means this plus 5 volt is connecting with this line. So this line, over this line, there is a plus 5 volt will be there. So this input is connected to this OR gate, and this input is also connected to this OR gate. None of this OR gate is connected with this line. So what happens? Output of this one. Output of this OR gate is going to be 0. So A is equal to 0. B is also going to be 0. Because this input is connected here, so one of the input is high, so output of the OR gate is going to be high, so C is equal to 1, and similarly D is also equal to 1. So you will be getting A, B, C, D is equal to 0, 0, 1, 1 conditions. If button 6 is going to be pressed, what will happen? This input is connected to this OR gate, and on this line this input is connected to this OR gate. So when this line is going to be activated plus 5 volt, that means output of this OR gate is going to be high and output of this OR gate is going to be high. So A, B, C, D is equal to 0, 1, 1, 0 will be there. If 9 is going to be pressed, you will see that this output is going to be high, and this output is connected to this OR gate. So this output is going to be high. So 1, 0, 0, 1 is going to be optic. Now this kind of circuitry we are not going to prepare with the OR gate and switches etc. manually, but instead of that the IC which is going to be available in TTL format, we are going to utilize that IC. The IC is 74147 is and pinout diagram etc. of this IC we are going to study. This IC is normally known as decimal to BCD encoder. The decimal inputs are x1 to x9, connect to the pin number 1 to 5 and 10 to the 13. That we can see that in the IC. The BCD output comes from the pin number 14, 6, 7 and 9. Pin number 16 is for the supply voltage and pin number 8 is for the ground. Pin number 15 is written no connection, means that is not utilized at all. You can see that this is that IC 74147. I think there is a problem. This IC is actually 7445. By mistake, it is printed 74147. You can see that in this IC. This IC is of 16 pin IC. Pin number 16 is connected with the VCC. Pin number 8 is connected with the grounds. Pin number 1 to pin number 5 they are utilized, and pin number 10 to pin number 13 they are utilized for decimal inputs x1 to x9. Pin number 14, pin number 6, 7 and 9 they are utilized for BCD outputs. Pin number 15 is not connected anywhere. This is a schematic circuit diagram of the same IC. Here on the left side, inputs are written. The inputs are shown with X1 to X9. And on the right hand side, the output are shown A, B, C, D. That is the BCD outputs. This is shown with the power supply plus 5 volt. VCC is supposed to be connected and ground is connected. Because this is a TTL, regulated plus 5 volt is required. Now, with the input and output in this schematic circuit diagram, you can see the bubble. What is the indication of this bubble? That input is going to be activated when that particular pin is going to be activated low. Then that particular digit is going to be activated. You can see that. And corresponding to that, you will get output. But output you are not going to get BCD, but you are going to get complement of BCD because bubbles are shown. The same thing is going to appear in the truth table of 7445. Here, when none of the switch is going to be closed, what happens? All inputs is going to be high. So none of the input is going to be activated. That means all output BCD output ABCD they are going to be in the high state. When X9 is going to be low, that means what happens? X9 is going to be activated. Corresponding to X9, the output will be L, H, H, L will be there. And if you complement this one, you will get 1001. That is corresponding to this, the BCD output is going to be 9. That means you are getting a complemented BCD output when that particular input is going to be activated. If X8 is going to be activated, then you are going to get L, H, H, H like this way. So from X9 to X1, when X1 is going to be activated, then you will be getting H, 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 L. Figure 4.26p shows how to draw 7445 on a schematic diagram. As usual, the bubbles indicate active low input and output. Table 4.5 is the truth table of 7445. Notice the following. When all X inputs are high, all outputs are high. So that means none of the input is going to be activated. When X9 is low, the ABCD output is L, H, H, L, equivalent to 9 if you complement the bit. When X8 is only low input, the ABCD is L, H, 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 equivalent to 8 if the bits are complemented. When X7 is only low input, ABCD becomes H, L, 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 equivalent to 7 if the bits are complemented. Continue like this through the rest of the truth table, and you can see that the active low decimal input is being converted to complemented BCD output. That means any one of the active decimal input can be made low, so it is going to be activated. Corresponding to that decimal input, the BCD output is going to be opted, but you are getting complemented BCD outputs. Incidentally, the 7445 is called priority encoder because it gives the priority to the highest order input. Priority encoder means if all more than one input is going to be activated, then it gives the priority. What will be the output? There is a confusion. If you consider that there is X1 to X9, all are activated, all are low. What happens? Which one? What will be the output? Output will be given priority to the highest order input. Which is the highest order input? X9 is the highest order input. So it gives the priority X9 to all others. And because of that, you will get the output is going to be L, H, H, L. So only X9 is going to be encoded. In other words, X9 has priority over all others. When X9 is going to be high, that means X9 is going to be inactive or it is disabled. That means What is the next highest input? X8 will be the next highest input in the priority, and it is going to be activated. And if X8 is going to be low, then output is going to be L, H, H, H. And if you complement that one, you will get 1000. That means you will get the encoded output is going to be BCD output corresponding to X8. Working your way through the table 4.5, you can see that the highest active low from X9 to X0 has priority and will control the encoding. The same thing you can see here in the truth table also. If you read this truth table in different way now, I'll show you. Here, see in this truth table, if x1 is going to be whatever it is, x means don't care. And in this one, x9 is going to be activated because that is only low. All other may be low or high, but what will be the output? It gives the output corresponding to x9 only because x9 is activated and it is highest order input. When x9 is going to be high, the highest order input is going to be x8. So whatever other inputs may be, either it is going to be low or high, it gives the priority to x8, and corresponding to x8, it will give the encoded output complement of the BCD of x8. It will be given, that is LHHH. And similarly, up to the last one, you can see that it gives the lowest priority to the x1 and it gives the highest priority to x9. Now, one example corresponding to this one. Let us see what is the ABCD output of figure 4.27 when button 6 is pressed. This is the circuitry which is connected like this. So, when the button 6 is going to be pressed, here plus 5 volt is connected through 1 kilo ohms resistance to each of the line. So, what happens when the switch is not going to be pressed? Another end of the switch is connected to the grounds. That means this end of the switch is just open circuit. That means when the switch is not connected or none of the switch is going to be pressed, what is the input? Input to all the inputs from x1 to x9 will be high because no current is passing through 1K, and hence whatever this potential is there, that potential is going to be appear over each of this line. So each of this line is going to be high, and what will be the output? All output ABCD is also going to be high. Now, whichever switch you are going to press, let us say if you press the switch number 3. So, when you press the switch number 3, this 5 volt is going, because of this 5 volt, this is a higher potential, but this is going to be connected with the ground, and hence the voltage will be dropped across this resistance, and here the potential is going to be 0. So, X3 line is going to be activated because it is a 0 volt or it is in a low state, and corresponding to X3 the output is going to be activated. What will be the output? Complement of BCD will be the output. Normally 0011. That means HHLL will be the output. Now you understand this example. You understand the figure. Now there are certain questions you can understand here. Solutions: when all switches are going to be open, that means x1 to x9 inputs are pulled up to high state plus 5 volt. A glance at table 4.5 indicates that ABCD output is going to be HHHH at that time. That is the truth table shows. When the switch 6 is going to be pressed, X6 input is grounded. Therefore, all X input are going to be high except X6. Table 4.5 indicates that ABCD output is HLLH, which is equivalent to 6 when the output bits are going to be complemented. So here you can see that X6 is going to be pressed, this line is going to be activated, and this line is going to be ground, and the X6 is going to be activated. Corresponding to that, you are getting BCD out. Now, next topic is exclusive OR gate. Normally, in basic logic gate, you are studying AND, OR, and NOT gate. That OR gate is known as inclusive OR gate. That means any one of the input or all of the input is high, then output is going to be high. That last condition, that all the input is going to be high, then output is going to be high, that is excluded. And that's why this is known as the exclusive OR gate. This is utilized in so many circuitry. The exclusive OR gate has high output only when the odd number of input is going to be high. This is just a definition of exclusive OR gate. So if you are having a two input exclusive OR gate, that means when the output is going to be high, when A and B is not going to be equal. So either A is going to be high or B is going to be high, then output is going to be high. But when A is equal to B, that is equal to either 0 or it is going to be 1, then output is going to be 0. So A is equal to 1, B is equal to 1, then output was 1, that was old OR gate. So that condition is excluded here. Now, how this circuit can be built up? You can see that this circuit can be built up. Here there is an input A. So after the input A, there is an inverter is given. So output of this inverter is A bar. So one of the input to this AND gate, upper AND gate is A bar. Another input is taken from another input B from here. It is taken directly. So input this OR gate is A bar B. Similarly, input to lower or AND gate is A directly taken, B is inverted, so B bar. So AB bar is the input to this one. Output of both this AND gate is the input of OR gate. One of the input is A bar B, another input is AB bar, and that will produce the output Y, and that Y is equal to A bar B plus AB bar. The upper AND gate forms the product A bar B, while the lower one produces AB bar. Therefore, the output of the OR gate, this is known as a Boolean expression for the OR gate also. So Y is equal to A bar B plus AB bar, or it can be also written as A direct sum of B. Here is what happens for different inputs. When A and B both are going to be low, both AND gates have low outputs. Therefore, the final output Y is going to be low. So, A is low, B is low. What happens? If you see the circuitry, A is low, so A bar is going to be high. But B is low, so output of that upper AND gate is going to be low. Lower AND gate, A is low, so output of the lower AND gate is also going to be low, because one of the input is low, the output is low. So both the input of the OR gate is low, so Y is going to be 0. If A is going to be high and B is going to be high, again A is high, so A bar is going to be low. B is high, so B bar is going to be low. So one of the input of both the AND gate is going to be low, so output is going to be low, and output of the Y OR gate Y is going to be low. Now, if A is low but B is high, what will happen? If A is low, B is high. A bar is going to be high, B is high. So both the input of upper AND gate is going to be high. So output of upper AND gate is going to be high. That is the input to the OR gate. So output is going to be high. A bar B is going to be high. So output Y is going to be high. If A is equal to 1 and B is equal to 0, then what will happen? Again the same thing. A is equal to 1. So lower AND gate A is equal to 1, B bar is going to be 1. So this output is going to be high and you will get high output. A high A and low B result in a final output that is going to be high. If both input are high, both AND gates have low outputs and final output is low. Table 4.6 shows the truth table for a two input exclusive OR gate. The output is high when A or B is high, but not when both are going to be high. This is important things. So in exclusive OR gate, output of the two input exclusive OR gate, when output is going to be high when A or B is high, but not when both are going to be high. That means it will compare the two inputs, and depending upon that, if the inputs are different, then and then only output is going to be high. If the inputs are going to be same, that is going to be 0 0 or 1 1, then the output is going to be low. In other words, output is 1 only when the inputs are different. This you can see that this is the truth table of exclusive OR gate. A is equal to 0, B is equal to 0, Y is equal to 0. A is equal to 1, B is equal to 1, Y is equal to 0. Here these two inputs are going to be different, so output is going to be high. This is the symbol of exclusive OR gate. That means normal OR gate plus there is another line is there. This indicates that A is equal to 1, B is equal to 1, that was equal to 1. That condition is excluded here. Figure 4.30 shows the symbol for a two-input exclusive OR gate. Whenever you see this symbol, remember the action. The output is high if either input is high, but not when both inputs are going to be high. Stated another way, input must be different to get the high output. Thank you, dear.